Okay, so let's get going. All right, so today we're going to, so we sort of finished this aside that we had about we're doing this model problem, right? And with the characteristic initial value problem for this nonlinear wave equation, so that I would introduce the ideas in a setting which is not like algebraically complicated. But now it's sort of that time that everyone fears, where it's time to sort of grow up and do the adult things. And you have to look at now we have to look at the Einstein equations. And what I want to, though I'm still going to try to ease into it. Notice I haven't ever, even though you're free to, of course, Google the things, but I haven't written on the board. I haven't done anything like write all the formulas for the double null equations, right? I'm trying to give you the smallest amount of information that you need in order to do each step. And I think that's a good way to sort of, if it's your first take it, then that's a good way to do it. Okay, so all right, so as a first step in this process, so we want to understand how basically the whole story that I gave about nonlinear waves and the characteristic initial value problem, we want to understand how that what's the corresponding story for the Einstein equations and the double null gauge. And the first step is this, I want to discuss the analog of this formal jet computation. So let's and I'll remind you what I mean by that. All right, so what did I mean by that? So for the wave equation case, this is basically the phone. So again, we're going to consider, let's look at some rectangle like this. So again, it doesn't really, I mean, without loss of generality, I can always call this guy u equals -1, say v equals 0. And what we saw for the wave equation, so if we had some wave equation, and then, I mean, we could really put something very general here, something just depending on nonlinearity, function, depend on the point. Right, so remember, so data in this case, so we would suppose that we have already specified, so if we know the restriction of psi to u equals -1, right? So remember, so if we know psi on u equals -1, of course, that means we know all of the dv derivatives of psi and all the angular derivatives of psi. And if we know psi and all derivatives at where the two hypersurfaces intersect. Right, that's natural because in the other direction, you would think you're going to pose the tangential behavior there. So, I mean, if you know everything along u equals -1, you have du's and you have angular derivatives. The only thing you're missing is dv. But at this sphere right here, where these two things intersect, you have dv. All right. So the point was that there was this observation that if you know this and you know this, then you can, the full jet meaning just all of the derivatives along this hypersurface of this are determined by solving inductively some ODEs, right? So in other words, you just look at the principal symbol of this, and you can write this as, you can write it as dv of du of psi equals sort of the stuff you know, very roughly. Okay. And then, so that was so to get so stuff you already know, so you could integrate this as, well, stuff you already know plus some function of du. There can be something which depends on d by du. All right, and so this is an ordinary differential equation for d by du of c. Because of the second point here, you know the initial data, and so this, you can solve this ODE. You can at least do it in a short distance. And I mean, without more information, of course, this thing could blow up if it's nonlinear, but whatever. We saw under favorable conditions, you can even solve it globally, blah, 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 blah. Okay, so what we want to do, what's the analog? So we want the analog for Einstein. Okay, so that's going to be the first goal. Now, before I do that, I'm going to, well, first of all, does that make sense? What are the goal that we want to do? So I'm going to pose, we're going to have, the analogies are going to be, we're going to pose some kind of tangential behavior of the Einstein equations. I told you already what that means. That means that you fix the metric things, the g slash, the lapse, and the shift along one of these hypersurfaces. The only requirement is that the Ricciarduri equation in the corresponding direction is satisfied. I'll say that again. And then, and that's it, basically. Well, then you need the thing over here. And then just from those things, I want sort of an inductive procedure, which allows me to compute the full jet of any double null of any of the unknown quantities that show up in the double null gauge, right? And well, such a thing will exist. Okay. And moreover, we'll see that it has the favorable, well, it corresponds to the case where you have a good nonlinearity. In other words, like you won't, it, it, it won't be possible to blow up, right? So the ODEs you get, well, in general, at every stage, you will solve some linear ODEs, which can grow exponentially, but cannot blow up. And that's one of the manifestations of what people often say in this business is this is a manifestation of null structure in the Einstein equations. Because it's, anyway. All right, but we need to finally say some more about the Einstein equations. Okay, so first of all, let's remind ourselves of the players. All right, so I can do this. So we said a lot of this already, but there's a lot of information in the double null equation, so it's okay to repeat a bit. All right, so these are the parts of the metric in the double null gauge, right? That's sort of the zeroth order things. And then you have things corresponding to some derivatives of this stuff, which is going to be, and I can even group them in some way. So we have omega bar, chi hat bar. I'll put the indices to indicate their tensor types. So that's a function, that's this tensor, and then we have trace chi, right? These were signature equal to, remember, signature is number of E3s minus number of E4s. These are all signature 1. Then we had this correspond roughly to, I'm just going to say that writing it takes a while, so let me just verbally say quick. Remember, this is the derivative in the E3 direction, i.e. think of the U direction of the lapse. Of course, there might be the shift vector in there. It's not exactly d by du. These are the second fundamental forms in the E3 direction of G slash. Okay. Then we have also Ricci coefficients. We have eta bar, and torsion. These are all 1 forms. These are all signature 0. These correspond to, so the torsion corresponds to basically a V derivative of the, well, you can set it up in different ways. I suppose actually the way, yeah, because you can put the shift in either the V direction or you can move there's some symmetry of like whether it is you see it in the U component is not orthogonal or the V component. Anyway, so in this situation where we're starting on U equals -1, it's sort of natural to make B vanish on U equals -1. That's natural. And then it would be natural to have that du of B equals torsion. Okay. Remember, maybe it's also useful if, it was a while ago, this issue of where this vector field, this B that shows up when you write the double null coordinate systems had to do with when we were defining the angle. We had these null hypersurfaces, and we had these angular coordinates, and you had some first sphere, and you wanted to sort of move the angular coordinates to all the other spheres, and it was basically a choice of if you go like, V then U or U then V. That's the asym. Picking one first and then the other one is what causes the shift to be in a different place. If just to jig your memory. Okay, so these are signature 0. And then we have basically the flip of all these quantities associated with 4. So omega chi hat of AB and trace chi. Okay, which just correspond to all of these ones, but in the 4 direction, these are all signature -1. Right? And so in particular, remember, so all quantities, these so-called Ricci coefficients, the signatures can only be absolute value less than 1. Then we had okay, yeah. Then there's sort of null curvature components. All right, so these are, so if we want to start from so we have alpha bar, A, B, beta bar, A, rho, I'll sort of put rho and sigma together because they kind of go together. Beta A and alpha AB. So these are various, just the curvature tensor projected into different parts of the underlying null frame. This is going to be signature equal to 2, signature equal to 1, signature equal to 0, signature equal to -1, signature equal to -2. Okay. So the curvature components have signatures whose absolute value is bounded by 2. All right. Okay, so now I want to say something a little more about what the various equations look like. Okay, so in a sense, we usually think of it as sort of two big sets of equations. In a sense, they're three, but the first set is sufficiently simple that we sort of don't we sort of de-emphasize it, which is to say that there are relations. I sort of already mentioned them in words when I was writing these down. Certain derivatives of the metric quantities are given by these ones, right? So well, the last one I didn't say was so torsion is a say u derivative of b, and then the eta and eta bars. Remember, these are just some combination, plus or minus combinations of the torsion with angular derivatives of the lapse. Okay, so somehow those equations are sufficiently simple that uh, you know can de-emphasize those. So the heart of the system is a set of equations, first of all, for these null structures, which, either sometimes these are derivatives in the four direction or the three direction or some angular operators. And these are generally, though I'm going to see in a minute, we can rewrite things. But the usual way you write it is, so remember, let's be very schematic first. So psi is, say, a Ricci coefficient. All right, I'm going to get a lot more specific in a second, but let's remember the schematic form. So very high level, a null structure equation looks like the following. You have either a nabla 4 derivative, a nabla 3 derivative, or some kind of angular operator. Those are all possibilities. Remember these, we do discuss these things. These are like you take the space-time covariant derivative and project, right, onto the spheres. All right, so this will be applied to one of your Ricci coefficients. And then in general, the kind of things that you can see, these are things that you might see. You might see a curvature component. Remember this capital, this is kind of not great notation for the board, but this corresponds to null curvature. You might see that. You might see some quadratic term in the Ricci coefficients. These psi's might be, are not. This is the class. It doesn't mean the same one, right? These things are always contracted with the metric on the thing. And then you also might see something, you might also see some angular operator applied to psi. That's the general form for the null structure equations. Now there's one little thing that I didn't say is that there's a guy which sort of doesn't fit totally here, but is a bit important, which is there's also the Gauss curvature of G slash, which we usually denote by K, right? And there's also an equation for, so there's a similar, and so there's also some equation for Gauss curvature, which takes this one. All right, and then the signature of K, if you think about it, should be 0. Because it's just G slash is a purely spherical thing, and then Gauss curvature is just taking spherical derivatives. Spherical derivatives don't change signature. Okay, so this I already said, right? Okay, so now what I want to do though is just get a lot more specific about what things show up, and I'm going to give you some information. All right, so the first one, and we've already seen this, if you had to pick one equation, which was the most important of the null structure equations, then that one would, I think there would be very little debate that equation, if you had to pick one, the most important one would be Ricci-Drake. This is the one behind, of course, the singularity theorems and such. Okay, so let me write that. This will be maybe the only one that I actually write the full definition of. We've also already seen this because I mentioned it when I talked about initial data for the characteristic initial value problem. You had to have a solution. This one had to sort of be solved already. All right, so that's the Ricci-Drake equation. Note again, the notations are kind of, if things are vague, it's because there's only one way it really makes sense. So if there's some norm squared of this chi-hat, that must be the norm computed with respect to G slash, right? This is an object that lives for each UV. This is an object, it's a symmetric trace-free 0,2 tensor on the sphere. So this norm is the sphere. So like I could write this, but we understand, so we don't need to write it. Okay, so that's Ricci-Drake equation here. Note one, there's something very that's unique about this equation is that there is no curvature term here, right? That's related also why it's a useful equation when you want to prove proving those incompleteness / singularity theorems of Hawking and Penrose. You don't need there's no curvature in this equation to mess things up. It's because sort of the natural curvature that shows up here in a general spacetime is, of course, Ricci curvature in the 4,4 direction, which if you're a vacuum is 0, right? I guess I maybe it just should have emphasized everything I'm doing is under this assumption, right? Okay, maybe that was worth saying. All right, so that's that. Then of course you have the corresponding equation in the three direction. Oh, this should be this. Sorry. All right. Okay, so that's that. Now, so those are the only ones that I really want to write explicitly. And the rest I'm going to give you a little more information about, but often I won't write explicitly. Because again, lots of things you can just determine by signature considerations will already give you a lot of will tell you a lot of information. Okay, so I've written those explicitly. I'm going to now sort of rewrite the in some sense write some of this information again. Okay, so in general, so let's go for both. So for trace, well, okay, I'll just say the following. So also for trace chi, so we also have an equation for nabla 3 of trace chi. Okay, and all I want to note here is that for this one, you have this curvature here. This one does have an angular derivative of a Ricci coefficient. And then you have this. And in fact, this coefficient that shows up here is the angular derivative that shows up here. It's eta. Yeah. So in fact, what you see is okay. That's some. So it's useful to know some. So a lot of these equations, I mean, this term is sort of not, this kind of angular derivative of a Ricci coefficient is not present in most of them. So it's useful to identify the few cases it shows up. Right. It causes some. It can cause some difficulties in some things. Anyway, all right. So that's trace chi. So we have an Abel-4 equation for trace chi. So that's that. All right. So then, well, there's of course there's the analog of trace chi bar. We'll give you some curvature, and this one basically is uh, yeah, basically it's the same. So again, this one you also have. Let me put this here. This one you also have the same structure, except now this one that comes up here, it's divergence of eta bar. Okay. Whatever. Okay, so fine. All right, so now let's look at chi hat. So chi hat satisfies just an equation like this. Right? You don't have that angular term in its Nabla-4 equation, but you do have a curvature term. Okay. Well, maybe actually as I do this, so again, the schematic expression, just to make sure we're on the same page. When I write capital psi, I mean, it could be some constant, right? It might be 5 times some curvature component, right? I'm just not writing the 5 or whatever. Okay. Also note that you can, again, just by signature considerations, the possible things that show up here are very there's not a lot of flexibility actually. So I mean, I could even just write. So here, there's actually only one possibility. Let's see why. Chi hat has signature -1, right? Because, well, just look at the table, right? Nabla-4 lowers the signature, so it's -2. The only thing this can be is something of -2, but there's only one curvature component of -2, which is alpha, and that is alpha. All right, so this is kind of thing. So you sort of okay. So then we have Nabla-3 of chi hat, and this is again of well, this one's interesting. So this one now doesn't have a curvature component actually. But you do see this, and you see that. And again, the angular derivative that shows up there. Again, it's not really important exactly what it is. I just want to say that the thing that's involved there is eta. I don't even think actually, it's always a bit unnatural because it's the form you have all the formulas, so you know all these things. But now that I think about it, I think for what we're going to do, it's actually irrelevant. You don't need to know what this term is, but anyway, just so you know. I'm trying to do this pedagogical strategy of give you as little information as possible about the equations so that you slowly get used to it. So maybe this was violated my strategy. I shouldn't have told you this. So you can wipe it from your brain. All right, and then you have the same. Then you have the corresponding. Well, I'll just write same for chi-hat bar. You flip everything, right? So, well, in this case, it's just really just the same, except this one will be eta bar for chi-hat bar, even though you're not supposed to know that. Okay, so that's what those equations look like. So now let's look at eta. So eta will satisfy an equation curvature that form, right? That's all I'm going to say about that. And then there's going to be an equation. This will satisfy an equation like this. Again, that's all I'm going to say. Again, what's the content of me writing this based on what I've said so far? Well, first of all, content is one, that there is such an equation, right? Because I didn't say that. It's not that every Ricci coefficient satisfies something with all of these, right? All right, and then the second content is that there's no angular derivative of something. All right, so that's, all right, there's some other equation for eta, but we're not going to use it, so I won't even write it. And then we have nabla 4 of omega bar equals something. And then you have just the sort of the flip, nabla 3 of omega equals again, equals this. All right, so you see, so the only ones where these angular derivatives appear are the ones with the second fundamental forms. Yeah, so that's that. And then we have so these are equations, yeah. Okay, these are some equations. Then there's some other equations which are often sort of grouped separately when people write them. Sorry, but I can't see the blackboard. Did you just, what's the issue?
Excuse me, Professor. I can see your first two black ball on the left, but I
No.
can't see your black ball on the right.
Yeah, no, I messed up, didn't I? There's some button you push, and they showed me how to do it, but I don't remember. Maybe oh, let's make it wild guess. Will that work?
Yes, it works. Thank you.
Oh, nice. It's dangerous to just push buttons, but sorry about that. Yeah, if I miss your chat in such a situation, just feel free to speak out. Okay, so what was I saying? Oh yeah, so there are these two sets. All right, so this is sort of, there's some ordinal structure equations which are sometimes written separately, and these are ones that come from looking at just taking the sphere, and you have the equations for if you have a hypersurface and an ambient spacetime, the curvature tensor of the not necessarily hypersurface, submanifold in ambient spacetime, the curvature of the ambient of the submanifold is related to the curvature of the ambient spacetime and stuff involving the second fundamental form. And it's like the Gauss-Codazzi equations. And so anyway, so working those out, in fact, taking some traces of those equations give you some other equations. So, and again, I'm going to write them schematically. So one of which is that you have an equation for, so this is not, so we haven't yet seen an example of an equation like this, of an angular derivative equals some stuff. So here's the first one. So we have, and we introduced these operators already. So you have this D2 is the divergence of chi hat. This equals, well, and now I'm going to write, so here's another equals something like this. Again, these things do not mean that the constant in the equation is 1. In fact, it's like 1/2, but. All right, so you get an equation like this. This is the one that follows from Codazzi, if you work it out, Codazzi on the sphere. Well, again, it's really a trace. I mean, you do Codazzi, the standard version relates like the curvature of tensor on the sphere to the ambient curvature. You don't know much about ambient curvature, but a suitable trace of that gives you Ricci curvature, and then you can get something. Okay, so all right, then you have the flip. All right, so the similar thing for everything flips. again, by signature considerations, this has to be beta, right? This is signature -1. Angular derivative doesn't do anything, so this has to be something at -1. The only option is beta. Just making sure we're remembering that those are constrained. All right, and then so those are Kadatzi equation, and then there's also the Gauss equation. The Gauss equation basically just says that the Gauss curvature is equal to some null curvature thing plus again some things. Again, by signature consideration. So this is the case where the signature doesn't tell you exactly what this thing is, but it tells you. So this has signature 0. So this has to be a curvature component of signature 0, but there are two of those, rho and sigma. In reality, the one that shows up is rho, but again, it won't, for what we're doing, won't matter. Okay, so those are the null structure equations. Yeah, questions? Make sense? It's just some equations. All right. Okay, so now, so I could tell you the curvature, but maybe again, on the principle of trying to like slowly titrate out the information. Let's pause. I'm not going to tell you about the equations involving curvature yet, which if you remember, those are derived from combining the Ricci equals 0 with the differentiated Bianchi equations, right? That gives you those equations for the null curvature components. So we'll review those in a second. But what I want to say now is something else. So I'll say something actually, which is often not emphasized in discussions of the double null gauge, but which is a little amusing. So this will just be an assertion. So, all right, so you have all these equations, right? And you see there are these C's that show up in different places. So sometimes some of these equations, have the same, the same C show up. Oh, that's not a question mark, it's an assertion. Have the same C show up. Right, again, you can see that just based on signature consideration. So for example, the Nabla-Foreb eta equation, eta signature 0, Nabla-Foreb signature makes it all signature -1. So that C has to be beta. But then I just talked about how in this divergence of chi-hat, there's also beta. Right, so using that, you could of course just say that, well, those two equations, I can remove beta from the system and write it as an equality of the Nabla-Foreb beta is given by something at divergence of chi-hat, right? So this is not what people basically ever do, but you can do this. All right, so you can actually, remove the all curvature from the system, basically using this. All right. And what's nice about that is, well, first of all, there's no curvature, it's like simpler. I'll tell you in a second why it's bad, but so that simplifies things, right? And in fact, so moreover, in this, the resulting system, you know, holding is actually equivalent. All right. So like I said, the point is not made very often because somehow, well, because this doesn't matter for what most people are doing, but it's sort of, I think it's conceptually a good thing to keep in mind. Yeah.
I thought we assumed that G of G was equal to 0.
Yeah. So now I'm saying, and so now.
Oh, when you remove.
Yeah. So all these things are derived under the assumption that Ricci G is equal to 0. And at the end, so under that, I said you can do this thing where basically every curvature component, well, not all of them. So yeah, so not every curvature component will appear twice. So in fact, and again, just from what I've written, you can see an example just based on signature. So Nabla-4 of chi-hat, we argued that by signature that had to be alpha on the right-hand side. But there's actually nowhere else alpha can even appear because of signature considerations. So that one, somehow you can't. So when you do this, so you can remove all from the system, and you just and you throw away equations, you just throw away equations where this shows up once. All right, and then the resulting system. So then you get something that doesn't involve curvature because I delete the Nablus-Forf chi-hat equation. And the resulting thing, that's something which you could say on a general spacetime that could hold. Because you could put a double null foliation in any spacetime and you could posit that these equations hold. And it turns out by just tracing all the computations that that's equivalent to the Einstein equations. If this is confusing, why I can throw away this thing, it's that, it's useful to think why is that? That seems weird. That's in reality, that's because that equation is sort of not, it's kind of just a definition of alpha, really. You can think of it that way. Because in general, on any, say, double null foliation, you have these second fundamental forms, and it's just in general the case that Nabla-4 of the second of the trace-free part of the second fundamental 4, you do some commutations, it's going to be equal to something involving nonlinear combination of Ricci coefficients and a certain curvature component, and that curvature component is alpha. So like that, so somehow there are things in here that have nothing to do with the Einstein equations, but we still want to use them because they relate derivatives of Ricci coefficients to curvature. Some things very much have to do with the Einstein equations, like Ricci-Dury equation. The fact that there's no curvature here, it's exactly because that when you take the trace of that thing, you would see this one very much has the Einstein equations. Okay. Makes sense? All good? Okay. So, all right. So now what I'm going to do is I'm just going to use this system to do my formal jet computation. All right. So everybody's good on Zoom? Yeah. All right. So now let's do the formal jet computation. All right. So our starting point. So let's assume. So we assume. Remember that we know what order do I usually write it? We know omega BA and G/AB. And then remember, once you know these, so along, well, let's say we know it along u equals -1. I'll just say it like this, and along v equals 0. Right? So that includes, so this includes this thing that when these two spheres intersect, we know them basically in all directions. Right? And then remember, just from this is enough to define, so in particular, things that just involve, because these quantities here are defined from these quantities only with derivatives in the, in the no, sorry, I did the wrong. I want to start here because we know things on u, so on u equals -1, the derivatives go in the v direction, right? So because we know these things, for example, on u equals -1, these, like this is just the like -1/2 times the dv derivative, well, of log of this, basically, right? Divided by the lapse again. All right, so therefore we know this automatically. We don't have to do anything. It's just, well, if you know a function of v, then you also know the v derivative of that function. That's all I'm saying. Similarly here, these are just basically the v derivative of g slash. All right, so we know these things. All right, so we'll know these. So we know also then omega chi hat and, all right. Okay, let's assume all right, let's assume that Ricci-Dury is satisfied. Let's assume the Ricci-Dury in the 4 direction, because of course there are 2 Ricci-Durys. Let's assume this is satisfied. Yeah, so let me give this thing a name. I don't know. Call this system the star. So that's the system where you take the null structure equations, and every time you see 2 of the same curvature components, you equate them. And if that doesn't happen, you throw the things away. Okay. So then I'm going to claim then star holding allows us to compute full jet of every other Ricci coefficient. So full jet of, well, the other one. So eta bar, torsion, and omega bar, chi hat bar, and trace chi bar along, and here's crucial, along all of u equals -1. All right, of course, there's a corresponding statement and on v equals 0, but it's all symmetric. All right, so again here, I'm saying all of this. That means that you don't have this ODE blow up that, I can do on all of the u equals -1. All right, so is the statement clear?
Of this system is overdetermined.
Yes. That's an issue. Yeah, I won't. That's an important thing. Well, I was gonna say something at the end. So the system determines things, and then so now what you'll say. So we'll go through why you can do that. But after having done that, you might say, well, all right. So I have this. Does the resulting thing satisfy, say, to infinite order at v u equals -1? Does it satisfy the Einstein equations? And that is in fact the case, but it's not because the equations are overdetermined. So this process, you will not, I'm going to give an algorithm for how to do this. That process will use a subset of the equations. And because of that, you could be worried. But what were we saying? Oh yeah, so I was saying, so there's a similar sort of, basically you can, I mean, I'm getting a little ahead of myself here, but yeah, basically there's some, you can show, what you show at the end is, so after you do this thing I'm saying, that there's some missing, there's some components of Ricci which you will have shown vanish. Then there'll be some other missing ones. Then you can show, basically using the differentiated Bianchi equations, that these extra Ricci components that you need to show that they vanish satisfy an ODE system. Then because sort of everything will be good on v equals 0, they'll initially sort of vanish if you do the same process I do on u equals -1, you do on v equals 0. So they'll initially vanish. And then then this ODE system will sort of imply that they vanish. You have to prove that, but you can. It's possible to do that at the level of the jet again. But I'm not going to give that argument. And moreover, I don't think you can find that argument written anywhere, but it is possible. Okay, any other questions? Nope. Okay, cool. Yeah, so let's do this. Okay, so yeah. We'll see how far we get. Yeah. So first of all, we know the lapse. So note that we know yeah, so keep in mind, so we know, because we know this along u equals -1, so to find, well, yeah, so to find this, or this, it suffices to find one of them. Right, that's because both eta and eta bar are equal to plus or minus torsion, and then you're just adding some angular derivative of the lapse. That's just the formulas. All right, and we know this, and we know angular derivatives of it already. Log u equals -1. The only thing we don't know about this, we don't know what d by du of the lapse is, but that doesn't show up doing that. All right, so I only have to consider one of these basically. Okay, so the natural thing is to look at the Nabla-4 equation for eta. All right, so let's look at Nabla-4 of eta. And what can I see on the right-hand side? Well, what can I see? Well, I can see things. Well, it turns out, so when you do this process, the substitution process, So we can go and we can look at this. So you can think about, so nabla 4, so first of all, you can of course see eta times eta. I mean, c times c. And then I did this curvature component substitution. So remember that curvature component that you see there, it has to be beta because eta is signature 0, nabla 4 is signature -1, and beta is the only one. All right, so then you can say, where else does beta appear in the system? And again, if you look just based on signature, the only other place it can show up is in that Kadazzi equation. So you see, so you're going to get, in other words, you just see angular derivatives of chi hat and trace chi and more things. So just again, just by what I wrote in signature, what we see here is basically, I'm writing it very schematically, just something like this.
Like not very because we don't know the bar.
I want an equation in the v direction
Oh, okay.
because I'm on u equals -1, so that variable along there is v equals 0. So I want to, of course, so I mean, so the point is like where, again, so where these two things intersect. So along at u equals -1, add v equals 0, because then I know everything. I can compute everything there. But then I want to integrate, solve something from there, and I need an equation in the 4 direction. And so the only, well, torch, it doesn't even show up anywhere here, right? There's no, so my only options are the nabla 3 for eta bar, nabla 4 for eta. So I'm immediately my only option is nabla 4 for eta. Okay, so I get this, and now, so these ones we know. So these things we already know, right? Okay, so now the question is, what can these be by signature consideration? So this, remember, so this is signature -1. These ones, so they have to, remember, signature is additive. So if you're going to add to -1, so remember the only possibilities for signature are 1, 0, and -1. So, I mean, they're not, if you add two numbers and you get -1, it can only be something of 0 times something plus -1, right? So this has to be, something, I'll write it like this, sigma something 0 plus something 1. Right, where this index means it has signature 0. So maybe I'll sometimes write, I'll put a sub s that will mean that, maybe I should sigma some, I don't know, a. So if I put an index like that, yeah, this is not, I'm sure, because there are other indices used. Yeah, capital Latin indices are on the sphere. So if I do it like this means the signature is a. This is a horrible notation. I don't like that. I shouldn't write it as an index. I should write it like this. Yeah, so let's do that. That's clear. That's not an index. All right, so if I write, all right, so sometimes if I want to denote what the signature of a generic Ricci coefficient is, I'll write it like this. Okay. Okay, so it has to be of this form, -1. All right. Okay. Now we say, but look, all the -1, the things that are signature -1, we know. But we know all, right? Because it's just those ones. It's exactly the ones that are already in the 4 direction. So in sigma of 0, that just equals any of these eta bar, or torsion. But I just argued that because we know this, because we know angular derivatives of the laps, these are just all equal to eta, well, up to some constant times eta plus C1 plus some other constant times this, and we know this. So the upshot is that this equation for eta is just a first order linear ODE for eta, because I know, right? So this is a linear ODE in the 4 direction. And I can pick, right, so the norm, of course, nabla 4 here is going to be it's just like 1 over the laps times the angular derivative and the covariant derivative in the dv direction. And then possibly there's one more thing you might complain about, which is you might say, oh, but shouldn't you convert the covariant derivative? What you really want to do is have a Lie derivative, right? Because you're going to solve the ODEs and coordinates. But again, the difference of I'll just say this in words, the difference of the Nobel 4, this covariant derivative in the 4 direction on the spheres and the Lie derivatives in the spheres. So if you, all right, so I'll write it like this. So if you have this in of some quantity, let's suppose we go up here. This is the same as just the Lie derivative plus, well, what? Well, I mean, okay, it may be, I sort of just introduced this SUV formalism a bit, but it's kind of what you think, right? I mean, the difference of these things just involves, the covariant derivative of d by d of one of these coordinate vectors of the coordinate frames with the d by dv. So this should be, so there's some things here like nabla for dv of EA, EB, there's some stuff like this roughly times this. But this is exactly just the second fundamental form, right? This is the norm. So this stuff, this is all, just chi, which we know too. So in other words, you don't have to worry about this thing about covariant derivatives in the 4 direction versus Lie derivative. That's fine. All right. So having made that comment, I'll now not worry about that difference. Okay. So the upshot is that this really is, it's of course a system. So eta is of course a tensor, right? So anyway, but so you can think of it as a first order system for ODs. And so it exists. So we get, and we know, so we know eta at u equals -1 intersect v equals 0 because we know everything there. And so this determines eta along all of u equals -1. And because of this comment, it determines all of these. All right. All right, so that example already illustrates the fundamental, like the kind of the tricks. Does that make sense? All right, so let's take a 10-minute break now. So let's reconvene at 4:10. All right, so we any questions so far? No? Good. Okay, so let's go to these other equations. Okay, so maybe I want to leave, it's good to have this table of the signatures, so let's leave that. And any questions on Zoom I should ask? No? All right. All right, so now we turn to, so that covered all the things of signature 0. So now let's turn to things of signature equal 1. Okay, so that's going to be all right, chi hat bar, yeah, trace chi and omega bar. Okay, so yeah. So now I realize, so there's something here. Oh, I just erased something. Okay. So now we're going to go through the same process. So we can again, so we have equations. For Nobel 4 of all these quantities. For okay. And again, the way I gave them to you, there were maybe some angular derivatives. Well, there were these curvature components, but now I asserted that it was possible to sort of sub out the curvature components to write everything back in terms of Ricci coefficient. So let's just go ahead and write the general form of what you could see basically. So what you end up with, remember, so you can see, so some kind of, write it like this, so some kind of angular derivative of a Ricci coefficient plus some kind of like this. All right, so we see this on all sides. Okay. And now again, we just do the same. All right, so there's something I was slightly doing under the rug there, which is that so in these equations, so these things are, this is signature 1, and then novel 4 of that lowers it. So these are all signature 0. So everything here, so these equations are all signature 0. Now, so when there was a curvature component on the right-hand side of a signature 0 equation, just by signature, that component could be rho or sigma. And so when you can't quite just abstractly say that the another signature 0 equation is the same curvature component, like I did with the beta, but it does work out, right? And in fact, you have equations, like you have for both rho and in fact, I mean, it works out for many reasons somehow. First of all, in the equations that we look at, only rho, that to derive these, you actually only need to look at rho. But in fact, both rho and sigma have expressions which relate them to angular derivatives of things plus something nonlinear or Gauss curvature. Yeah, so I should write yeah, so we also will allow some Gauss. Well, we can just throw it in everywhere. Right, because Gauss curvature, remember, is signature 0. But Gauss curvature, of course, if we know G slash, we know it's Gauss curvature. Okay, so this is, I claim you just do that from that general nonsense, you know that you have some things like this. So okay. All right, so now let's do the analysis. All right, so I mean, you sort of also start to see some even more patterns even within this abstract way of looking at it, right? I mean, now before it lowers things by 1, and so you already know that I don't even need to give specific numbers. I mean, this lowers things by 1, and Angular doesn't do anything. So whatever this is something lower. And so I've already computed it, even before I say 0 and -1, right? That's it. Okay, but fine. This is all signature. This is so these are signature 0. So this is something signature 0. So these are all in my notation. These all have to be psi 0, but psi 0 is exactly what I already computed. So those are fine. Those are known. All right, and then so these things have to add up. So these things have to add up to 0. So there are two possibilities here. So psi dot psi, this can equal two different things. So this could be a 0 signature contracted with something 0, or it could be something of 1 contracted with something -1. And so this one we know already because we computed for the same reason we know this already. And this one, again, we know already we know this. So this is so again, so the upshot, and we also know, and these we know, because these are determined from the G slash. So the upshot is you get sort of a big ODE system, right? So you have some, let's say, so you have all of these things. This is all some system where you have some, so think of this as a vector or whatever, then you have some matrix applied to that same vector. Plus none. So again, it's a linear ODE, right? This is some known matrix. That's because everything, the way it couples back is linear. So note some things about that. First of all, that it's not you see the importance of doing the inductive signature thing consideration, because if you sort of tried to do the 0 and the 1 at the same time, you might get afraid of this. This looks like a possibly bad nonlinear term, because this allows the same thing times the same thing. Remember with the wave equation, we said we don't want to see du squared, right? So because the Einstein equations are a system, it's not the question of what's a good or bad nonlinearity is a little more complicated. You have to think about what it's feeding into and stuff. And so this, even though this is a psi 0 times a psi 0, it's not dangerous because the equation it shows up in is sort of further down. Somehow it's like by the time you need to estimate this, there's some other equation where it would have already been okay. All right. This is a common kind of structure that you see in the Einstein equations. That sort of either there's something more reminiscent of that wave equation. So either you see things like the du times dv and it's okay, or you see something bad, but somehow there's some way to set up an inductive structure where you sort of already estimated it before it came up. Okay, it's very common. Not just also it's a common type of nonlinear structure in hyperbolic PD that shows up a lot. Okay, so we can do this. So we solve for, so we can solve, all right, so we get all of these. All right, so that's nice. Okay, so now, so that allows us to compute all of the Ricci coefficients. And, well, yeah, the claim is that that's basically, well, all right, then there are different ways to proceed. All right, but what's missing now? So what's missing is that we want to compute, say, further derivatives of them. So we need, there are different ways to look at this. One possibility, you can take advantage of some of these quantities have there are direct equations for nabla 3 of them. So you can sort of, if you want to know nabla 3 derivatives, you can use those equations. So that's one. You don't actually even need to use that, but let me just remark on that. So I'm leaving that up. Oh, I should go on here. All right, so now what remains to compute, say nabla 3, derivatives of all the Ricci coefficients. Now, and I'm saying there's sort of two. So one thing that's just worth noting is that many of the equations simply satisfy nabla 3 sort of derivatives. So, well, yeah. I mean, so for example, like there's just an equation for nabla 3 of omega. And so you can use that to do some stuff. But there's some equations for which, it doesn't work. So for example, there's some, and we'll see this kind of, the relevance of this will come up later when we do the a priori estimates for the characteristic initial value problem. It's not the case that every Ricci coefficient sort of satisfies an alpha 3 equation. And if it did, that would sort of be nice. So this was the thing. So when we did, just to show how this is a little different than kind of the wave equation case. So in the wave equation case, remember when we were doing the estimates for the derivatives of the low norm estimates for the wave equation, we had, you could do it in sort of two steps where you integrate it, like you had du of dv equals some stuff. This you can integrate in that way, and then you could just do the fundamental theorem of calculus in the other way and sort of get all of the psi's. Well, I guess you could try to do something like that here, but just because of the geometric nature of the system like that, that procedure where you sort of get, the hard step you integrate in in the U direction, and that's where we had some smallness and that was useful. That's a little, you don't quite like it's a little harder to directly employ that here. Nevertheless, it's still for the ones where you have an alpha 3 derivative, it's good to keep that in mind. So anyway, so I wanted to say, so there's some set of things where it's really getting, so if you want to know, well, yeah, so alpha 3 derivative, that's in the equation. So alpha 3 derivative of trace chi, that's just in the equation, et cetera, et cetera. So the ones that don't satisfy alpha 3 equations are going to be, so omega bar does not satisfy an alpha 3 equation. Well, I mean, eta similarly doesn't. And chi hat bar also doesn't, with a caveat. So it doesn't. So what do I need a caveat here? So of course, if you look at those original equations that I wrote, alpha 3 of chi hat bar, I mean, I did write it in the null structure equations, but this is one where so the alpha 3 of chi hat bar, you had something of this form. So why am I saying for the context of this, it doesn't? That was because this was one of those ones where you can't substitute this curvature component for anywhere else, because this one, basically this is going to be alpha bar. Again, you can see that because this is signature 1, alpha 3 of it is signature 2, sorry. Oh, no, that's right, yeah. So this is signature 2, and alpha bar is the only one of signature 2. So you know that this has to be alpha bar on the right-hand side, but there's no other equation that's signature 2 if you just look at them. Well, there would be. The only other one that could be is Raichaduri, but we know that Raichaduri doesn't have any curvature component. So it's not possible to, this is sort of like, you can't use this for formal computation. What you should think, this is really just a definition of alpha bar. It's just saying that alpha bar is by definition this derivative. So it's not useful. Okay, so in that sense, you also don't have these equations. Okay, so given that you don't have direct equations for all of the unknowns, what's the strategy? The natural strategy is just to basically run through the same system that we already did and just apply Nobel 3 to it, right? Just commute the equations to Nobel 3. And basically, you know, just looking at the clock, basically everything will work the same. But the only thing I need to tell you about is sort of, you need some formula for commuting, basically. So we just need to, all right, so because of these, we need to commute, we need to apply, Nobel 3. Well, in fact, eventually apply, it's an inductive argument in the number of Nobel 3s. You're going to commute all of the equations with Nobel 3s to the various Nobel 4 equations. All right, for these unknowns. All right, so all the other ones, again, are fine automatically because you have good equations. So for example, all these ones that, so I guess this whole process, kind of the inductor, it was very important that we knew the s equals -1 to begin with, right? This omega. Okay, but all of those, I should say, all of those are good. In other words, like there isn't well, I wrote that you already have this one you have, and you already have this does equal something, and Nobel 3 of trace chi also equals something. So it's sort of this thing that you already know, the signature -1, that structure is still there. So you just have to, there are these extra ones that you have to find again. And again, you're going to just try to do the same structure, just commute them with Nobel 4. You just need some formula for Nobel 4. But in fact, somehow all I really have to tell you about Nobel 4 is that it also satisfies signature. I mean, I just give you the rough form, and then it will satisfy signature conservation, and so the same kind of logic will work. So very roughly, so if you have something like this, some quantity, well, let me write this even just as, I'll just say, just very schematically, like some tensorial quantity in your commuting here, what are you going to get? Well, in general, what you get, so you can see some curvature component contracted with this. That makes sense because you're commuting covariant derivatives. So expect to see some curvature. then you can see Ricci dot Ricci with this thing. You can see and you can see kind of there's some Ricci times nabla 3 of the thing plus you might see some Ricci times nabla 4 of the thing, and then you might see sort of the other way around, nabla 4 of the thing plus Ricci of nabla 3 of the thing. All right. Again, I don't. Again, they're completely explicit formulas if you want. I mean, you can be very precise what this is, but you just need to know this. And then everything this respects signature considerations. So for example, just again, let's as an exercise in our signature brains, we know this quantity here. So these things are the same. So a nabla 3 and a nabla 4. So together, this is sort of a signature 0 operation because 4 lowers you by 1 signature, upgrades you by 1. So therefore, this quantity C can only be rho or sigma. All right? Because those are the only signature zeros. Oh, and I guess the other thing maybe I should have said, well, yeah. There was one other remark. Well, I mean, it's sort of implicit in, I mean, in what we did before, but also, so at this stage where I said it remains to compute these, it's also useful to note that basically rho, sigma, beta, and beta bar, these can all be recovered from, you know, angular, you only need to take angular derivatives, from at most just angular derivatives of basically, well, either these things or your Ricci coefficients. So once we did that first stage, you can go back to the equations and you get all of these ones. Why do I mention that? I mention that because, for example, when you do this nabla 3-4 commutation just by signature considerations, this one has to be of rho or sigma, but we know rho and sigma actually from the first stage. All right, and then basically just for the sake of time, maybe I'll just stop there, but I'll say you use this formula and then the exact same kind of considerations we did. All right, so now I mean it's a little more tedious. You have to, but it's essentially it's the same structure works, and you're able to so you'll get nabla 4 equations. You'll have nabla 4 of nabla 3 of this, and that will satisfy some ODE. And again, you do the same inductive procedure by you start with the signature 0 ones, and then you do these ones, and you're able to compute everything. Make sense? Yeah.
Practically, we already know rho and sigma. I feel like it already shows something back at the nabla 3 equation for omega. Because nabla 3 of omega is like signature 0, so it has to involve rho or sigma. Like when we were saying that nabla 3 of omega is something we all find with.
Yeah, well, I guess, yeah, I mean, sure. But I mean, there I was saying, yeah, it's true that on nabla 3 of this, and the standard way you write it, there's a rho. But then rho, you can, with the Gauss equation, you do that substitution I mentioned. So then you can rewrite this where it's Gauss curvature. But yeah, but then you could also remember that in fact, that means you know rho. So everything you say about the null structure equation is always overdetermined. Every statement includes some other statement. Yeah. Okay. Yeah, I think that's what I want to say for now about that. Okay, so so just some sort of philosophical points. So first of all, we already talked about, because we had this question about, well, these equations are overdetermined, so does this really solve the Einstein equations? It turns out that if you do this, maybe let me, yeah, so let's go here. Well, let me write down the claim specifically. Yeah, I mean, it's a little like, Well, maybe I won't actually write down a precise claim because I mean, you have to be a little careful with, okay, of course, this solved for all the Ricci coefficients, and then you'll want to solve for, I mean, really the metric is just determined by the metric coefficients. So I should give you like a way so you do this computation, you get some formulas for what the Ricci coefficients to satisfy. Then, okay, you want to actually have some space-time, which is like, that really means something for, you want to write everything in terms of just the jet of the lapse shift in G slash. And anyway, you can do that, and in such a way that eventually, if you run a propagation of constraints argument, it will satisfy to infinite order. But okay, but let me just suppress that just for, it just gets technical to state it, and it's not actually that important. But what I do want to emphasize is that this is just that this philosophically, I mean, this tells you, so this is very general, this is very useful in many situations. This is very useful in many different situations. And this goes a long way to the usefulness of the double null gauge for studying all sorts of problems about Einstein equations. So, it just tells you that once you know, so given tangential behavior along a null hypersurface, forget about the characteristic initial value problem, just any situation. And also you can have all sorts of, null hypersurface could be infinite. I mean, this structure, what I showed, like this fact, and then, sort of, again, the full jet, so you have general tangential behavior. Assume that Raichaduri is okay. So assume that's okay. Then the rest, the full jet, is just linear ODEs. Right? That's a highly non-trivial statement, but that's very useful. I mean, so somehow, and so in many situations, it's not obvious. So you can try to compute things. So we'll see. This philosophy is very important. So we may have forgotten what the point of this course was, right? At some point, we're going to get back to self-similar things. And the point is, like, you're trying to construct something. And this abstract procedure tells you, like, once you just set some tangential data, you solve Raichaduri somewhere, maybe you, okay, I'm getting a little ahead of myself, but you set it up in such a way that just those things look self-similar somehow. Then there's a procedure. You don't need to, like, for everything else, you can just run this machine and just solve some ODEs and just see what you get. And that they're going to be these linear ODEs, and depending on, so in general, they're these linear ODEs. Of course, linear ODE might be hard to solve, but in many situations, they're not just like they're ODEs that you really can understand very well. Right? And okay, so that will be this. So somehow this will be very important when we get to sort of the final application of all these ideas back to self-similarity that closes sort of the course. But not just there. Also, for example, very famous work of Christodoulou on understanding formation of trapped surfaces. I mean, again, this sort of inductive structure, this fact that you sort of initialize something about tangential behavior, and then there's this inductive structure where you get the rest of all of the elements of the double null gauge via signature, and is crucial to how the whole thing works. Of course, and it might be phrased differently, but you can understand the things in that way, sort of. Anyway, so this is just, it's hard to overestimate the significance of this kind of inductive structure allowing you to solve everything. All right, it's absolutely not true for a random system of nonlinear hyperbolic equations, right? There could be so many things could go wrong in what I did. Okay, so that's that. All right, so now I wanted to sort of, close that part of the discussion, because now I want to write out the more general form of or write out a little more about all the Bianchi equations. Where are we? Yeah. Okay. So, and again, I'm just going to write it. I'm going to write just the things that matter, and I'm going to use these. Yeah. Anyway, I'm just going to write out the principal symbols, and then the nonlinearities are just going to be written in the schematic form. And again, signature. It'll turn out that all we need to know about them is signature. Okay. So Bianchi. So, and then I'll remind you what I've told you already. So what we talked about before So the Bianchi equations, so these are referred to as we call them the Bianchi equations for the curvature. So again, for alpha, beta, and then in some sense, it makes sense to consider rho and sigma together. We'll see why in a second. So all of these things, right? Okay, so let's write these out. Okay, like maybe again, the general form is going to be that you'll have nabla 3 or nabla 4 is going to be applied. We'll write it like this. So you'll have nabla 3 applied to some curvature component is going to equal some angular operator applied to another one, plus nonlinear terms that are all of the form Ricci coefficient times null curvature component. And then this will come with a nabla 4 equation times that applied to this one equals minus the where do we put the star? Forgot. At something like this. Plus again, this kind of nonlinear. So this is what we talked about before. And we talked about how this structure allows you to prove that, do something like an energy estimate. So now that we had got that experience with the wave equations, maybe that discussion we made about doing energy estimates here hopefully makes more sense. So the same way that we multiplied the wave equation by du or dv, integrated by parts and got things, this adjoint structure here allows us to do the same thing here, except with the caveat that this is a first order system. So you should think of the wave equation as second order, but think of it as like a first order system for du and dv. And that if you have an equation for du dv, you can write it as du of v equals something and also dv of du equals something. And if you make that analogy, it's very similar. So in other words, that you multiply. So if this is like so if you think that this represents dv of the solution, you multiply this by dv, that's a total derivative, and this, whatever. Anyway, that's the analogy. Okay, so that's we discussed this is roughly. This was the rough form, but now I want to just tell you explicitly, how it works. Let's leave. Well, I guess I can erase the bottom of this. Okay, and right, so here we go. So the first equation, so the first Bianchi pair. So the first pair, well, I'll just write it. So the first pair involves alpha and beta. So maybe again, just to remind you of the types of tensors they are, I'll put in the notation. And so this takes the form nabla 3 of alpha equals, well, I'm just going to put, because sometimes there's some constant. So C will just denote some constant in general. So it's going to be times some equals some constant times, and here we get the adjoint of D2. So remember, D2 is the divergence. D2 takes a symmetric trace-free tensor and takes the divergence of it, gives you a one form, and then D2 star is the adjoint of that. All right, so that's, well, I guess with the definitions I gave, I think in reality what you see is this. So C will just denote some positive constant. Some positive constants. So CI denotes some positive constants, which aren't too important because you can just you can always divide your thing by C. All right, and then we can write this as nabla 4 of B equals, and then this one will be D2 of alpha. So contractions. All right, so that's the first so-called first Bianchi pair, right, for alpha and beta. So one thing, again, what's useful to keep in mind when you're looking at these equations, when we do these null energy estimates, that whether or not you're in a nabla 3 or nabla 4 tells you which flux you will get. So remember the way that you do the energy estimates here is that you would multiply the first by alpha, multiply the second by beta, and integrate by parts, right? And so when we multiply the first one by alpha, you have nabla 3 of alpha times alpha. You can write that as nabla 3 of roughly alpha squared, right? Or pretend they're all scalars. Forget about the tensor thing for a second. Again, we'll probably next lecture when we actually do the a priori estimates, I'll explain that in more detail. But for now, pretend they're scalars for that part. So then you have nabla 3 of alpha squared. So then when you integrate that, you're going to integrate in the u direction. Remember, so you're going to integrate over all of space-time and then apply the fundamental theorem of calculus in the u direction. So you're going to get, at the end of the day, an integral. The fluxes, the energy fluxes you control for alpha will be in the v direction. That's similar to how when you do the energy estimates, when you multiply it by dv and then you integrate it in u, the energy dv only appeared integrated in that, the null derivatives, the fluxes you got are exactly where they're tangential, right? So dv you only got integral in the v direction, and du only came integrated in the u direction. Right? So there's a similar structure here. And how they appear tells you which flux shows up in a given Bianchi pair. What we'll see is that these ones, so alpha and alpha bar, which are sometimes called the extremal curvature components, they each show up in only one Bianchi pair. So this is the only one where alpha shows up. So that means that alpha, you only have a flux in this v direction. In the same way, you should think for the wave equation, you think alpha is like dv of the solution. So that means that one also only showed up there. Beta shows up in both. So you should think beta is more like an angular derivative. Angular derivative of the solution shows up in both fluxes. So often sort of, subtle issues, involve alpha or alpha bar somehow. Okay, so that's the first pair. So the second pair is, so then you have a beta, or maybe, let me just go over here. Okay, so then we have beta, and you'll see in a second why I'm putting the rho and sigma together. So these ones, okay, depending on, what definition did I use? Oh, it's written a little weirdly. Yeah. Okay. So here's what you're going to get. I'll just write it out. I'll write out the operator. So you're going to get nabla 4 of beta is going to equal. No, sorry, not nabla 4. Nabla 4 showed up there. So like I said, so all the ones except alpha and alpha bar, every other curvature component will have some pair where it shows up as a nabla 4 and somewhere it shows up as a nabla 3. That's why you get both fluxes. So in this case, you're going to have nabla 4, and then you have angular derivatives. Let me put these in. So you have angular derivative of rho plus this, well, I'll write this out, plus this, basically the curl of sigma, and then you have plus these, right? So this is sort of related to this operator d star 1 that we talked about in the last lecture, but note the sign is different. That's because, well, you'll see in a second when I write the next one, you'll see why. All right, so then we have that, so nabla 4 of, which one do I want to write first? I guess sigma. So nabla 4 of sigma, this one is equal minus the divergence. I'll put the slash for the divergence of Hodge star. Well, I guess let me write it with the indices. So, all right, so this sigma is given by the divergence of the curl of B. All right, and then we have nabla 4 of rho is equal to is written to the divergence of, well, this is of course, anyway, is the divergence of B. All right, so because of these, it's written a little differently. So this is, of course, intimately related to that d star 1 operator and the d star 1 adjoint. It's just written because I sort of take, instead of writing it as a div as a div curl. This part is like div and curl of the unknown. It's written as you like hot star the unknown and then do the div. But anyway, they're all related up to a sign. And again, this operators are going to be the L2 adjoint of these operators. In other words, that integration by part structure works out. Yeah. Okay. And so again, so now this one will give you, so there you got U fluxes for beta. Here you'll get V fluxes for beta. And this one will give you U fluxes for sigma and rho. Okay, so that's that one. And then you get rho, sigma, and beta bar. And well, basically you just flip everything. Right, so this is going to be, so nabla 3 of rho equals minus divergence of beta bar plus this, and then you have nabla 3. So you see rho and sigma sort of, there's a set, rho and sigma sort of always come together. There's a sense in which they're kind of one quantity, really. Yeah, nabla 3 of this is equal to minus, again, div of, take this hot star of that plus that, and then so beta bar will then satisfy nabla 4 of beta bar equals minus so this is A minus A of rho plus a curl. All right. All right, so it's really just some kind of symmetric thing with the other one. All right, and then finally, the final Bianchi pair is beta bar and alpha bar. Right, and then finally we get beta bar and alpha bar, and so this one you're going to get nabla 3 of, just looking at this for what, I mean the constants don't really matter, but yeah, minus this divergence plus again this, and then you get nabla 4 of alpha bar AB equals that well that operator I guess, so what's the constant minus equals I think this is wait, it's just 2 times the star of, all right, that's okay. Okay. So that's that. All right, so hopefully now with the, so from the example that we did with the nonlinear waves, so now you can imagine how you know, similar arguments would work with the Einstein equation. So basically, again, so I'm just going to, I'm only going to discuss for the, so for the, now we're ready now to do sort of the proof, or what I want to cover of the proof of local existence for the characteristic initial value problem. And the main part that I'm going to, well, this jet computation is part of it. And now the other part that I want to discuss is I'm going to discuss how you do that bootstrap argument, because that's really the heart of the matter. There's this other thing about how you actually set up all the local existence arguments. That's a little sort of just for the sake of time, so that we get to you know, so that we don't run out of lectures without ever getting to self-similarity. I'm going to sort of close that off. You know, there's some extra complications there because of this overdeterminedness of the Einstein equations, and you have to do this so-called propagation of constraints arguments. In a sense that those are sort of, you know, once you understand how that works in other contexts, it's not really that different here. The parts that I'm describing to you are really the heart of the matter. All right. So now let me just say it quickly in words, and then we'll discuss sort of where we need to what kind of special structure we need to understand, and let's see if signature does it for us. All right. The punchline is it will. All right. So we know that there's going to be a high norms and low norms, right? So and now so the high norms you can think of, well, in particular involve, we're going to take a lot of angular derivatives of curvature to energy estimates, right? So those are just going to be we're just going to do separately energy estimates for all these things, right? We're allowed to put in these exponential weights again. We always have that flexibility. Okay, that's a useful trick. All right, and then we'll have this low norms, which are going to be, you know, soup norms of L2s on spheres. So we're going to have, right? So we'll have some kind of high norm. All right, so again, so we have some n, very, very big. And roughly speaking, our high norms are going to be sort of, you'll have integrals over u equals some constant. So for each fixed u, you have integrals in v. So this will involve, and so we'll have something like angular, I'm going to write it like something like this is like the induced angular covariant derivative. So up to n derivatives of, so we can have either alpha, beta, rho, or sigma, right? But we don't see alpha bar because there's a 4 equation, alpha bar only gets integrated along constant v hypersurfaces. All right, so this will be, one of the things in the high norm, and then you'll have plus, so there'll be some soup. So soup over all the possible constant u's. Then we'll have a similar thing, soup over c of all over v equals c up to, well, again, this is really like sum over j less than n, right? And then we have similarly sum over j, and now here we get beta, rho, sigma, and here we can put alpha bar, right? So again, in the analogy, so it's very important whenever you do things for Einstein equations, basically, is you have some analogy with a simpler nonlinear wave in mind. That's basically how almost literally everything that I know that's proven, there's some story like that that helps you organize the argument, right? So it's very important here. So we're keeping in mind, this is like dv of the solution. This is like du, and these are like angular derivatives, okay? And it's a pretty good analogy. All right, and then we have then there's going to be a low norm. Okay. You could say, well, what about, is it a little weird? Why am I not estimating the Ricci coefficients at all there? It turns out that I don't need to, but it's actually possible. So that would be natural to have a similar thing where you put Ricci coefficients and you do one more angular derivative. Because curvature is like if you think about the equations where curvature is one derivative of Ricci, so they should also show up in the angular derivative in the high norm, but with one extra derivative maybe. It turns out that for this particular problem we're doing, you don't need that. In general, there's a way to do that, but it's something more complicated. All right, so in the first pass at these techniques, it's nice to not worry about that. All right, then the low norm is going to be, well, basically, now is going to be soups over u and v of integrals of this, again, so here we might now we can put any curvature component. So again, we know that we can't go all the way up to n, but if you remember how it works, in reality, you just lose sort of one derivative, right? Because if remember we had when we did these soup norms, well, we did it in a way that lost more than one derivative because anyway. But you might imagine that. So already just maybe at the expense of getting slightly ahead of ourselves. So suppose you've done some energy estimates and you want to prove those like these soup norms on the spheres. So even for curvature, so you could go to an equation like this, right? So let's say I've already controlled this in in L2. I can just try to integrate this, right, to control this on like a sphere. And I can do that, all of these equations. I mean, maybe this one I have to go in the other direction, but I can always play that game if I control these on spheres. So if I control these fluxes already, I integrate and I control this sort of, this would be like the soup of this and the in the u direction by some integral of this in u. And then I can always do Cauchy-Schwarz to control that in L2 and by an energy. So you might think, I'm just saying, you might think it's reasonable to do this for all j up to just losing one derivative, is all I'm saying. Because you will lose one when you do that process. The right-hand side, if you do that process here, the right-hand side involves an angular derivative. So you can't go all the way up. There's also something I sort of just did quickly without remarking on it, which is I only wrote angular derivatives here. I'm not commuting with the 3 or the 4. It turns out that that works and it's convenient. Okay. All right, so I can do that. Then it turns out I'm also going to do the same. I'm also going to throw in a sup over uv. And then here we're going to also on all of these things, and I'm going to put any angular derivative. So now I'm going to go all the way up to n, and then I'm going to just do the Ricci coefficients. Like I said, so I said secretly, if you just count derivatives, you would think that it makes sense to put the Ricci coefficients here with n plus 1. I told you it sort of turns out you just don't need to because of, I mean, in some sense, it's because of how this structure of these things, that these happen when you write it in the standard way. It's always the case that this is a Ricci coefficient times the null curvature component. There are other ways to write these equations, which are useful in other, for other applications. And then where sometimes you see a Ricci coefficient times an angular derivative of a Ricci coefficient. And if you write it that way, then you do need to prove some other estimates. But we can do it with the simpler way. We don't need to. All right, so we don't have those, but keeping in mind that in principle, that would be the right high norm. This is sort of the right low norm. And again, sort of at the very first pass, where are these things proved from? These are proved from because, schematically, you have things like Ricci coefficient, equals curvature plus, okay, something nonlinear. But again, so this, if you control this in n derivatives, integrate it, by integrating these equations, you should be able to control n derivatives of this in a sup of uv integral in the sphere. Just the same way that it's the same logic behind this, really. Right. So again, there's some derivative loss because in principle, you should be able to go up to n plus 1. All right. And basically, these are the norms that we want to do. And sort of the things that could go wrong are kind of the same things that could go wrong, which is that we're going to make this bootstrap assumption. And, but the thing is, whenever we use the bootstrap, we want to see some smallness. We want to see an epsilon times the bootstrap. That's what makes it work, right? And the enemy, so if we remember, what was an enemy in the previous thing? Enemy was seeing something like du squared, right? So all right, so let me just go a few more minutes. So the enemy for the nonlinear wave was, for example, this, right? So now what's the analogous enemy here? So the analogous enemy here would be something like sort of alpha squared, but of course that doesn't quite make sense because you can't possibly see alpha bar squared, but it's like a maximal signature sort of something. So like in here, so you have nabla 4 of alpha bar. So you might be afraid of something, so you can't see, there are no nonlinear combinations of curvature, that doesn't show up, but something bad. So what would be bad? Well, something that's like as du as possible. So that would be something of like, chi hat bar times alpha bar or something. Because alpha bar is really a derivative of chi hat bar. Right? And so this would be bad. But again, signature tells you it doesn't happen. Because this is an alpha 4 equation. So this lowers things by 1. So this thing is signature 2. So this thing is signature 1. And so, well, it's quite the opposite, in fact. So not only can you not see this, you have to see the only thing, like you could only see this. Because if you see alpha bar back, you have to see it with something of signature 1. Right? So that's the analog of the not seeing du of c squared in the equations. Right? And then there's similar structures that will occur in the when we go and we estimate Ricci coefficients. So again, there's going to be this game. So basically everything. So okay, we'll go over this again later. So things that satisfy nabla 3 equations are good. So for Ricci coefficients, if this is basically just good automatically. So this is like we saw when we did the wave equation. We wrote it as du of dv equals some stuff. And well, there we still needed to use some structure, but you can kind of think here, you're just going to integrate stuff. And okay, it still could be bad if you see, there could be the one curvature component which isn't in that flux, but let me forget about that. But otherwise, this is good because that direction is small, remember? That's where you have the epsilon distance. And so, basically you can just, it's very easy to use the bootstrap here. And epsilon just eats everything. But we saw when we did this formal jet computation that not everything has this thing. So there's some quantities that we're going to have to do this. And then those quantities, what you're afraid of is that when you go to estimate them, you see nabla 4 of eta equals eta squared, for example, because then that can blow up, or plus or minus, whatever. That's this Riccati blow up. That's like the df dt equals f squared, right? But you see, and just in the structure that we discovered when we did the formal jet computations, we have already verified that this bad thing doesn't happen, right? Because we saw that basically you do eta first. When you do eta, everything, because of signature, was linear. And then you go to the chi-hat, you go to the other quantities, the chi-hat bar, trace chi bar, and omega bar. And then those things could see eta squared, but you already estimated eta, so it's fine. And then you solve linear coupling. So so in fact, we've already seen a crucial structure while we did the jet computation. It was a crucial structure which will allow this other argument also to work. But okay, we'll put all that. So basically, those are the kind of things, and we'll put that all together, and that'll allow us to run this kind of bootstrap argument. All right, I guess I'll end there. I'll hang around a few minutes, I guess, for questions, but we'll end the formal thing.